They're symmetrical parabolic vertical curves. Okay. So basic equation of a parabola is, my purple's getting ready to die. Y equals ax squared plus bx plus c. Look vaguely familiar? That's the formula for a parabola. Okay. So what's going to happen to us, though, is it's going to get translated and say that the elevation of a station is going to be equal to, instead of C, we're going to call that the elevation of PVC, elevation of the point of vertical curvature, plus, we'll call this at a B, we'll call that G1 x plus G1 x plus G2 minus G1 over 2L x squared, where G2 minus G1 over 2L takes the place of A.
PVC stands for?
Point of vertical curvature. So I'll go ahead and draw a curve for you and label it. Now you'll see different nomenclatures again. You might see this as PVC, you might see that as beginning of vertical curve or end of vertical curve. But point of vertical curvature, point of vertical intersection, point of vertical tangency. The grade coming into this is G1. The grade coming out of this is G2 given in percentages. Okay, so a percentage means change per hundreds of feet, right? So if you see something that says 5%, then what that means is you have 5 feet of change in every 100 feet. In a decimal format, that would be 0.05.
The BBC and EBC are beginning and end.
Yeah, but typically PVC will go with PVT, and BBC would go with EBC. Yeah.
Is it the same thing?
Same thing. Depends on which book you're looking at or which diagram, or resources you're using. Most plans I've ever worked off use the PVC, PVT terminology. So from the PVI forward to the PVT and backward to the PVC is the same distance. Okay, so and that length of curve is not measured. So in circular curves, we measure length of curve based on an arc length, correct? Okay, L equals pi r I over 180. In vertical curves, we measure the length of the vertical curve based on the station difference between the beginning of the curve and the end of the curve. Okay? It's not what the parabolic length of that actually is. It's just the length of those station differences. So here's what this equation gives you graphically. If you're looking for the elevation of any station, and I'll say this is the station I'm looking for, it's going to say that if I start at the elevation of the beginning of the vertical curve, and I go a distance x, which is the change in stations between this point and the PVC multiplied by G1, that gives me a slope times a distance, which gives me a point on that vertical tangent line. So this from the PVC to this point is G1x. What G2 minus G1 over 2L times x squared is this gap distance from that vertical tangent line back down to the curve. Whether that's here or whether that's here. Okay?
So keep setting it.
Okay. No, that's fine. So to find any point on the curve, so just so that this doesn't just turn into another bunch of equations that don't make any sense, right? It's like, well, what does it mean? It's like, okay, if I want the elevation of any station, then I start at the known elevation that the curve starts at, and then I add the quantity G1x, which gives me an elevation, okay, change up on this tangent line, on that vertical tangent line, which is where that green dot is. But I want something on the center line of that profile, and so this distance from the vertical tangent back down to the curve is identified by this quantity of G2 minus G1 over 2L x squared. So when you're solving these, what you're typically doing is this value right here, you're going to crunch that in and store it somewhere, because you're going to use it for every station you have to solve for, because it doesn't change. G2, G1, and G2 are given, and your L length is given. So that's the number that you keep pulling back up and using it with your changing X stations as you advance, through the curve.
Is X just like whatever your station is that you're looking?
It's it's that station minus the PVC station. It's the distance from the PVC to that.
The length arc.
Yeah.
That's
Well, but it's not an arc length. It's just a linear station difference.
horizontal distance.
It is in fact a horizontal
Like
distance.
the chord.
Don't even think of it like that. It's just it just represents the change in station from the PVC to the station you're trying to solve for. Because so here's the other thing. So just
So that big L, it's the same as it ever was. See, that's all horizontal movement.
no, absolutely not.
Okay.
Has no correlation to L out of your circular curves.
Okay.